evening and welcome to Tinkering with Edkelar. In the last two episodes I disassembled, cleaned and mostly reassembled this HP 9825A here. But to my disappointment it wouldn't show any signs of life on the outside. Mind you, the CPU showed activity, the start memory line and all the data lines were bursting with activity as soon as the reset signal went away. That tells me that the CPU is trying to work and even that some data flows through the system, but no display and no apparent keyboard activity. And to top it off, when cleaning the print head, the ribbon cable just fell off, because the strain relief came pre-broken. Now, after hitting this low point in the process, I had to put the printer aside for a bit to keep both mine and stagehand's blood pressure low. So let's see how the digital side continues. Now it's time for some low-level debugging. I do see some activity emanating from the CPU after all. So where to connect the logic analyzer? I found the easiest way to do that was the two bus transceivers inside the system ROM. These are directly connecting to the memory bus and collecting other signals from around the main PCB. They provide some insights on what might be going on. Now, let's have a quick look at what I'm doing here. I hooked into the memory bus lines and the STM signal. STM is start memory, which indicates that the CPU wants to access memory. When this line goes low, the current value on the bus is the address that the CPU wants to access. In this case here, 00040. All values are in octal in the documentation, so for easier comparison, I kept it like that too. Address 40 is the boot instruction in the ROM. As is evident near the end of the memory cycle here, the ROM returns 164041. The CPU reads location 41, which returns 10000. This combination of words is a far jump to the actual bootloader code. Looks good so far. Thankfully, HP had the whole device patented. And that patent included a rather complete instruction manual as well as the system source code for reference. At the startup location, 10000 octal, or the middle set of chips in the ROM cartridge, we have a very primitive code that is polling a single bit from the KDP. That bit is set when the reset button is down. In other words, the first few instructions detect if we have a hot or a cold boot. Without the KDP connected, it will always assume a hot boot and fail to initialize properly. The next part in the code is detecting how much RAM is installed. Here's where I found out that the two RAM modules I have are both somehow broken. One is completely bogging down the data bus and the other is failing in 2 bits, returning slightly different values than what was written. I did find a replacement 16 KB board and ordered it. Originally I wanted it to use for a 32 KB configuration, but knowing now that this will overlap with some ROMs, I just want the 24 KB version going again. So hopefully I can make a working 8 KB module from my 16 and 8 ones. Now what's going on? I followed the machine level instructions for quite a while and eventually it read wrong words from the system ROM. Weird. Wrong, but not always the same wrong. But always the upper 8 bits. To diagnose further, I wired up a few lines from my Arduino Mega and hooked up the ROM directly. The resulting memory dump showed quite a few differences to the expected values. No rhyme or reason, just the upper half of the second bank had bit errors over some blocks. And I even caught it changing values on repeated reads once. So, that chip is bad. So, new ROM? According to my reverse-engineered ROM chip pinout, these are masked ROMs of the early days, and according to TI, the TMS 2532 EEPROMs should be drop-in compatible. Well, almost. I tested it. The original uses both chip select lines of the ROM, active high and active low. One is for the ROM select and the other is for bank select. So without adding any additional chips, I need both of them. But the EEPROM is not playing along. It only has the active low enable line. Bummer. New idea. I am going to replace all of the ROMs in here with a new pair of 32 kilobyte EEPROMs. I got quite a few of these around, and if I don't need any bank switching, I can do with just one chip enabled line. I just need to wire them up with a few botches and get all the correct bits into the right location. At first I was confident and soldered the two ROMs directly to the old PCB. Sockets wouldn't fit to the enclosure. It was quite a few botch wires to reroute the signals for the new EEPROMs, but it seems to work. And of course, eventually, something was off in the EEPROMs and I needed to update the code. Which is when I decided to rework that board with sockets. I think this needs some repair pants. And after updating the ROMs once more and using the replacement RAM board, here we go, another test. Woo! Fancy pants helped. I can type commands and it does execute things. Yes! Well, at least until I wanted to edit the input line and tried out the insert button. That one reliably crashed my system. Turns out that I missed exactly a few bytes of wrong system code, which are, surprise, the jump table for the insert key. Whenever I pressed it, the system would jump into a completely no-code area in RAM and do random things. Now there's still a bit of a problem here. Whenever I do something with the RAM PCB, the first few power-on attempts fail miserably. I get either nothing on the display, as if no RAM was installed, or I get a line of triangles with the busy LED. I could not narrow that down yet, because every time it happens, as soon as I hook up some diagnostic tools, it is gone and keeps working until the next time I do something with the RAM PCB. I already wiggled all the connections. No clue what's causing it. Assembling the printer next. sorting out the different screws. Every use has its own size. Sheesh. Now to the next issue, the print head. I tried soldering the wires together, but these seem to be some sort of steel wires and they wouldn't take any solder. The two alternatives I can think of are: Option 1. I use my spot welder to reconnect the wires. Now, while this might work for the wire, I am not sure if it's a good idea for the chip inside the print head. In theory, it shouldn't matter, since there isn't any current or voltage going into the chip, but one never knows. I don't like to use sappy things next to my irreplaceable microchips. Option 2. Fix the cable in place and use several dabs of conductive paint to reconnect the lines. So option 2 it is. I'm fixing the strain relief first. I need to get the cable aligned as good as possible, making sure the plastic bar holds it in place, while repairing the broken peg with the old melting plastic together method. After applying about 10 layers of conductive paint, let's give it a try. Yeah, not yet. The wires needed a few nudges to reduce the contact resistance, but after another round of conductive paint, yes! And at long last, the tape mechanism. I'm gluing the new Capstan roller on the drum. Mounting the tape detection switches. And the spring-loaded roller for holding the tape. And finally, the ejection mechanism. Now to the elephant in the room, the tapes. These are just as old as the devices and have developed some issues. The one I have here as a first example has previously been used, and I hoped to be able to recover what was on it. The cartridges are very similar to the later ones that are known as QIC. I remember making backups on QIC 80 tapes. These have a driving belt loop strung around against the two spools and a driving wheel. When the capstan turns that wheel, the tape is transported from one take-up spool to the other by the friction between the driving belt and the tape rolls. The main problem here is the drive belt is made of a stretchy material, which ages just like most tape drive belts are. Not well at all. You can see that the belt has become stuck to the tape and it is falling apart into several pieces. Now that would not be a huge problem, there are known replacements, but the problem here is that it takes the oxide layer with it, leaving the blank carrier tape behind on the actual data tape. And if that isn't enough already, this particular tape is also stuck to itself and similarly peels off most of the data layer when spooling. So this one is going to be my test piece. Anyone out there who has a 9815 I/O program somewhere? If that is a standard thing. I found a pack of new old stock tapes on eBay. At least the tape itself is in good nick in these. There are silicone bands available that would work as new drive belts. I had to order them via a friend in Germany since they wouldn't ship to Austria for some annoying reason. Anyhow, thanks Luri, and here's the new belt. As mentioned, the transport belt took off the coating in the beginning area of the tapes. This means that the drive doesn't properly detect the end of the tape and is quite a bit confused. To fix this, one needs to shorten the tape a bit and punch new index holes so that the rewind function knows where to stop. Otherwise, it will spool all the tape onto one wheel. These holes form a specific pattern, so here goes. To keep the tape as strong as possible, I'm starting with tiny holes. I can always make them larger if needed. Winding up the slack and closing the lid. While the RAM cooperates, I'm trying out the tape drive. Rewind. And marking a file. The whole tape operation is rather low level. Let's look at the details for a moment. First off, the tape has 2 tracks. Modern versions, like the mentioned QIC80, would have quite a few more tracks, but this is strictly track 0 and 1. A bit like a 2-sided floppy in that way. You can select the track in software with the trk command, but here's where the comfort ends. To use the tape, you have to allocate files on it first. These are sequentially numbered from 0 to whatever and are put on the tape with only a small gap for tape speed tolerances. In other words, you need to make your file large enough for whatever you want to put in it and can't change the size without overwriting anything from that file to the end of the tape. Really low level indeed. I tried creating a few files on track 0 and it worked just fine, but when switching to track 1 and rewinding again, the drive pulled all the tape on one spool. I must try again with better sized holes. Now, while the RAM decides to work, I'm keying in a program. Usagi Electric created a list of computation times for simplified text-based Mandelbrot set. So I sat down and converted the code to HPL and made it fit the printer. 16 characters with 17 lines. I saved the program to tape several times. With the random crashes, I could at least incrementally type it in. Here's a quick overview of it. I am using the string ROM to keep one line of the result in a string variable and print one line at a time. After the start message and 2 empty lines, I run the X and Y loop. Note that the 9825 has only 26 variables, A to Z. That makes it a bit easier to write formulas, as you can omit the multiplication operator like on paper. And also note that HP uses equal assignments in the for loop, but an arrow operator for regular assignments. The design seems a bit rough. I'm adding a character based on the computed value to the string. Oh, and another thing is that there seems to be no break or exit for construct that I can find, so I'm using a bit of goto logic and set the count variable manually for an early out. If the pixel loop exited early, we are in water, so we need a space instead. Printing the line, starting with an empty string again, and continue until all the lines are printed. Takes about 20 seconds to compute and print. Certainly much faster than my basic programmable calculators, which are in the minute range for about the same size output. The mark command takes the number of files and their length in bytes. It can also return the last created file number as an output parameter. This is useful for writing tools that need to store results on tape. To save the current program, we need to know how many bytes we need. That's when the list command comes in handy. It displays the size of the program at the end. Using list -1 will show just that, without printing any line. The erase tape ERT command will erase a track from the current location. This is a good idea when overwriting existing data, otherwise the tape logic might find old file headers when going between tracks. To find out where the problem with my RAM PCBs is, I rewired my Arduino a bit, soldered a connector to an adapter, and made myself a RAM tester. Granted, this isn't going to stress test the RAM nearly as good as it should, but at least there is some activity to check for broken chips. And indeed, one bus transceiver had a stuck bit and was pulling the data bus line low. I swapped over an equal chip from the other PCB, but it's not changing much. So I'll go back to the real device and hook up the logic analyzer to the RAM side of things. And quite a bit of even more logic analyzing later, I saw writing 10063 to address 77511 returned a value of 10163 when read back later. Finally, a smoking gun. That would mean that bit 6 on the upper memory bank is shot. And after probing bit 6 in the memory board, I now know that the line is pretty much always at ground level, which is weird because it would mean that the bit is 0, not 1, but the lack of activity on that bit is telling. Quite a few trials and swapped RAM chips and bus drivers later, I found out that it must be the PCB trace between the RAM outputs and the bus driver. Because when I lift all 3 pins and connect them via jumpers, it works. Not the foggiest of clues what happens with the trace though. I'll just add a botch wire and be done with it for now. Since both of the other RAM PCBs are still not working, I'm pondering to make myself a RAM replacement PCB. As in, connecting a set of SRAMs rather than DRAMs. That should cut down on the component count, 12-volt current draw and cooling requirements. Also, it could have a jumper to select the 8, 24 or 32 kilobyte versions then. Now, the system ROM with the sockets is not fitting inside the tray anymore. Soldering them on the underside is also not a solution since the PCB is dead center in the available space. So, custom replacement PCB it is. And after a bit of work in KiCad, here we are. And nothing. What's wrong now? Turns out that the design rule checker of KiCad needs its priorities adjusted. The first page of the report shows stuff like thermal rule violations, which I don't care about. But missing connections? Those are small print on page 2. There was one data bit and almost all ground connections missing. Botch galore again. Now it works. Did I misplace that mounting hole too? No, HP did. These screws are ever so slightly offset. I'll make it fit for now. I will order properly fitting, no bodge PCBs when I order my next batch. The ROM modules get a good scrub on the outside. I would love to take a peek, but the cartridges are held together with a set of metal pins. I expect these are one-time push-in types to prevent opening. I could probably open them, but not without cosmetic damage, so I leave that for later, if at all. I also got myself an HPIB adapter, a must-have, and a parallel I/O module. There's plenty of documentation for the HPIB one around, but nothing but marketing stuff for the parallel I/O. While I wait for an old manual to arrive, I'll start with the HPIB one. The adapter is almost a computer in its own right. It has a small CPU, ROM and I/O chips. After giving it a quick cleanup, especially the grimy cable, let's try it out. Some of these chips have been replaced before. I'm putting on the HP digital to analog converter again. It is nice and easy to control for an example. Wiring up, adding the I/O ROM, and let's go! Each I/O module is configured with an address. For the HPIB, the default is 7. It maps the module to one of the I/O addresses. The keyboard, display, printer and tape controller inside the unit use addresses 0, 1 and 16. So plugins can pick anything from 2 to 15. On a personal note, 16 must be a software thing. The address bus only has 4 bits, so 0 to 15 is the valid range physically. And the KDP also only decodes one address. Now, to write to an HPIB device, we generally use the WRT or write command. It takes the target address, think like a file handle, and the value or values to write as ASCII text. The ASCII input command is called read. There is also a binary read and write available, but since most GPIB devices use ASCII commands, WRT and read are just fine. My AD converter is set up with address 2 and 3, so let's put it in the correct mode. Sending control character to 703, that is interface 7, bus address 3. And then, just to make things more interesting, using variable x, set to 1234 and writing that to address 702, the data port of the DA converter. And here we are. Nice. Now to something special. As you can see here, the cover of the printer originally had something glued on the inside. At first I thought it might have been a cover, but the press pictures in the catalogs show there is a little booklet stored in here. Browsing through Mark's archive again, I found a rough scan. The error code reference. And a day of fiddling with Inkscape and various printouts later, I have a nice reproduction. Since I couldn't see just how the booklet was originally held in place, I came up with this little cover plate myself. Let's see how that holds up. And another reproduction. There was also a quick reference manual which had a comprehensive list of all the HPL commands and even some I/O register details, but like the error booklet, the scan quality was not up to my standards. Another day and a half later, looks fine. In the comments to part 1, somebody suggested a 3D printed clip for the capacitors on the power supply. So why not? Looks much better indeed, and still is reversible if needed. I saved the Mandelbrot code to tape a few days before. Now let's try to reload it. It loads without errors, which seems good. To my knowledge, there's some checksums involved here. And run. Oh, what does error 22 mean? Improper dimension specification? Oh, wait, the strings ROM. I forgot to put it back in. Whoops, let's try that again, shall we? Now, bottom line, the system ROM had a bad chip and the RAM modules were fried. I still have no clue why the KDP chip wasn't doing anything before, but it sure is working fine now. Knock on wood. And that's it for the main project around the 9825A. I'm sure it will make an appearance on the channel again at some time. There are at least 2 follow-up projects here, which should make for a combined update video eventually. The RAM replacement and the breadboard interface for the parallel I/O adapter. But for now, let's move on to other projects from the pile again. I hope you enjoyed this restoration and repair project. See you next time! I saved the Mandelbrot code I didn't save it from tape, I saved it to tape and I want to load it from tape. Darn it.